delighted to introduce the 2013 John von Neumann lecturer, Stan Osher. The John von Neumann lecture is SIAM's flagship lecture. Is awarded to a mathematician or to a scientist in another field who has made distinguished contributions to pure or applied mathematics. Stanley Osher is professor of mathematics, computer science, and electrical engineering at UCLA. He's also an associate director of the NSF-funded Institute for Pure and Applied Mathematics at UCLA. He has infinitely many awards and distinctions, so I'll just name a few. I need to give him time to give his talk. So Osher has been elected to the U.S. National Academy of Science and the American Academy of Arts and Sciences. He was awarded the SIAM Pioneer Prize at the 2003 SIAM Conference and the Ralph E. Kleinman Prize in 2005. He was awarded honorary doctoral degrees by the École Normale Supérieure de Cachan in France in 2006 and Hong Kong Baptist University in 2009. He's a SIAM Fellow. The 2013 John von Neumann Lecture Prize awarded to Stan Osher in recognition for his extraordinary, influential, and wide-ranging contributions to the computational sciences and engineering. Since 1970, Stan Osher has been a leader in developing mathematics and algorithms, including essentially non-oscillatory methods for hyperbolic conservation laws, level set methods for front tracking, an L1 and TV methods for image processing, tomography, and optimization. He has worked with an exceptionally large range of students, postdocs, and other collaborators, and his algorithms are used by scientists and engineers around the world. And the title of his talk is What Sparsity and L1 Optimization Can Do for You. Steph.
Okay. Well, I don't have to say it's a great honor to be here, be associated with von Neumann and SIAM. And I'm going to talk about sparsity and L1 optimization and apply it to some new areas that are a little bit unusual, perhaps. So here's what we're going to talk about. Sparse solvers for multiscale PDE, and some analysis, and Hamilton-Jacobi equations, would you believe, have a link to L1 compressive sensing. And then there's a new method for getting compressed modes for variational problems in mathematical physics. And finally, we will have some fun with video compressive sensing, hopefully, if there's time. Okay? So at the beginning, we're a little bit more serious. I was told to be serious. I was warned to be serious, actually, by some people. Okay, so we will start with sparse solvers for multiscale PDE, a serious topic. Joint work with Wes Kaflish, Hayden Schaefer, Corey Hauk. The idea is to do homogenization numerically, automatically in some sense. You'll see what I mean by that. The goal is to solve problems that have varying phenomenon. You want to accurately represent the dynamics while being computationally efficient, and you want to do it sort of automatically, not problem dependent. Okay? So this is a very classical problem. I'll tell you what it is in a minute. We're looking at dynamic equations which have multiple scales, which occurs all over the place. For example, homogenization of linear PDE, elliptic, parabolic, hyperbolic, and even, God help us, turbulence, which is a dangerous topic, so I won't talk much about it. So the problem is there is a high-frequency part of the solution that you would like to get a handle on without resolving everything. And the high frequencies are all over the place. They're not, they're not localized. So the idea is somehow to localize everything. And it turns out to be very, very simple, and there's not too much theory, so we need help. We're going to form a sparse approximation to the true dynamics through L1 optimization. The idea is to compress the information at every time step and only propagate, we're going to talk about time-dependent problems, and only propagate important terms. And we're going to use very elementary notions that arise in L1 optimization. And the moral of the story, by the way, is L1 is as easy as L2, and it's better. The only nonlinear step in L1 is this shrink operator, as you will see, and we do it over and over and over again. So when you solve these L1 type problems, you're really solving a whole bunch of least squares problems, usually in the middle of which you do a shrink. And I'll tell you what that means. That's the only nonlinear step. And it converges real fast for various reasons that based on luck. The L1V is wonderful. We want the V. We do not want to round the V. The absolute value is important. We don't want to round it. Very important. Okay, so here we go. So the problem we're talking about now is ut is f of u. Are you still working on that? Somebody wants to ask me. Okay. U of xt, see, I have to be funny, is equal to a linear, we expand in a linear combination of basis functions, which I usually don't advocate at all for numerical purposes. And f can be almost anything, differential, integral, nonlinear, blah, blah, blah. The basis can be Legendre, Fourier, Chebyshev. I can say all these things because we're speculating, but it actually works for a whole bunch of problems involving Fourier, which you will see in a second. Okay. So we're going to do the most simple possible method, which is like forward Euler. So we have the following idea. We have un plus 1. If there was no p over there, that would be forward Euler, and the simplest possible ODE solver. And it's some kind of, f of un is some kind of approximation to the true solution. And standard projection might be on the low frequency, low wave number stuff. That's not what we're going to do, by God, not at all. The p here is quite nonlinear, but extremely simple. Okay, you can go home and program this. I can't, but you could. It's easy. Okay. All right, so there is some recent work by Runberg, Dobuchy, and Zhao, which is a little bit different and it's a little more special, but worth mentioning. They use a special projection onto the k largest magnitude Fourier coefficients. This is different. Here's what we do. We do the following. We take the update of the linear combination of phis. Remember that the solution is at every time step is a linear combination of these phi j's. I was going to point at the, here they are, okay, minus what we got by updating. And we minimize the L1 norm. This is the sum of the phi j's. This should be little L1, but when I write little L1, people think I mean 11. So the title of the talk would have been 11 sparsity or something. Okay. Plus 1 over 2 lambda, blah, blah, blah. The L1 norm is complex numbers. The L1 norm is this. And we're going to get some non-zero coefficients. So we're going to minimize this thing. And it's easy. Okay, and this I do this about 6 times a day or an hour or something. This is a very popular thing to do these days. Okay? All right. So if you have an expansion in terms of these Fourier coefficients, then you're doing a scalar optimization. You can think of this component by component. This is this bunch of CJs. And the minimum of this, if you don't know by now, you will know by the end of my talk ad nauseum. It's the shrink operator. So you minimize a constant C, the absolute value of it, plus C minus a given constant, and you get the shrink operator. Soft shrinkage. Okay, what is that? I mean, you can do it by hand. It's a trivial thing, but it's very important. The shrink operator is the following. You take the magnitude of this complex number, you subtract lambda, if you shrink with respect to lambda, take the max of that with 0, and then point it in the direction you were pointing at. Okay, so you just shove it closer to 0. No matter, even if it's bigger than lambda, you still shrink it, which annoys people, but you do it anyway. And if it's less than lambda, you make it 0. And this is what that optimization is. And that's the whole caboodle for this thing. Watch carefully. You'll see what this does for this wonderful problem. First of all, we do it by applying p to the sum rather than, if we do it this way, it doesn't work. lambda should be small. Numerical analysis 101 says you don't make an error bigger than dt to some power, right? So if you can't shrink it a lot because you'll be killing the accuracy and maybe even making it inaccurate. So you have to have some power of dt. And the accuracy depends on the number of basis terms. And the shrinkage operator is a contraction map in everything. If you look at it, it's a straight line, which is moved closer to the origin. Okay, and then there's a jump and this goes down. Okay. So we're going to do a whole bunch of partial differential equations, and we will automatically homogenize these guys, doing almost no work, nothing, zero. And you get results which are surprisingly good. And I want to figure out why one of these days. So take PDEs with periodic boundary conditions, use Fourier method with u hat being the transform of u, k is the frequency, but you can do more complicated things. Okay? And we start out with a baby PDE, which is linear hyperbolic, which used to be my favorite equation, except I didn't care so much about the oscillatory part. But anyway, we have ut plus a of two space scales, x and x over epsilon u sub x. A is highly oscillatory. That's all there is to it. Baby problem, periodic. We use a scheme which I would smack my students for using, which is on the border of being unstable, so it's not a good scheme. There's no dissipation. It's leapfrog. And then we shrink, and the world is ours. That's the moral of the story. Shrink and the world is yours. Okay, so here is the true solution, and this is a one-dimensional problem, so we can resolve the heck out of it, so we know the right answer. And we compare this method with the right answer, and you can see they're right on top of each other. And if, God forbid, we were chopping low frequencies, low wave numbers, we'd get bad answers, which is what people sometimes do in Fourier methods. They just keep the lowest wave numbers. That's not what we're doing. We're taking the magnitude of every coefficient and shrinking it. And if we start out with sparse data, we keep sparse data. We will see. And you can see that these few modes represent the solution. And this kind of periodicity is unsurprising because A has that periodic structure. So this baby little trick seems to give you the right answer. And it generalizes like crazy. So with 3% sparsity, we have the same kind of accuracy you would have without the shrinkage term. Okay, so all you got to do is expand in a Fourier basis, assuming the solution is ultimately sparse in a Fourier basis, and then shrink step by step. And that works for much more complicated problems, as I will show you. Okay. So here is the classical, people write books about this problem. This is where homogenization sort of started. Parabolic, A is strictly positive, so it's a nice parabolic equation, x and x over epsilon. This also covers the elliptic case because you can solve it by steady state, driving at the steady state, or you can create a basis using this equation and then expand in that basis. Okay? So for update, we do again a stupid scheme, which I would smack somebody for using. It's almost unstable. You take A, convolve it with IK Fourier, and then multiply by IK, and then upward, and then update. So it's a spectral method. And then you project, and lo and behold, you're right on the money. And with about 3 to 5% of the coefficients, you get rid of all this crap. Sorry, all this stuff. And coefficient looks like this, and you have automatically homogenized this guy. Nothing. I mean, there's really nothing to it. You just take your standard spectral method and apply L1 minimization in a diagonal fashion. So what about more complicated problems, you ask? Well, luckily nature gives us u dot grad u all over the place, right? Okay? So you can actually do that. You can take the Fourier coefficients of u dot grad u and figure out where they are. If you were doing e to the u or something, it would be impossible. But for u dot grad u, you just take the Fourier coefficients, do the same kind of thing, assemble them, update and truncate by this shrinkage business. So what we did is basically Berger's equation with diffusion. Now, again, if you have a shock, Fourier methods are not going to work, although people try and they make them work with crazy tricks. But you need a lot of Fourier coefficients to resolve a discontinuity. You don't want that. So we round it out a little bit by adding viscosity. We don't recommend this for shocks. We recommend other stuff. Okay. And we use Runge-Kutta 2, which is Yoon's method, standard finite difference method. And then we do the shrinkage business, and here we are. Okay, again, this is the kind of mistakes you would make if you truncate the red stuff, if you truncated by wave number. On the other hand, this is what you get right on the money by doing what we're supposed to be doing. Here you see the Fourier coefficients that we keep, which are the correct ones. And over here you see what happens if you just keep low wave numbers. Okay. So this stuff works also for Berger's with big enough viscosity, with some mild viscosity. Okay. And yeah, okay. And here is a little bit of an attempt to do some real physics. Here's the vorticity equation with a forcing function which is oscillatory. Oh, thank you. Do I look like I need it? I don't know. I do need it. Okay. So what makes this thing oscillatory is F. We're putting in some oscillations. Okay. This is easy to do with a spectral method because there's lots of Fourier transforms that get diagonalized with Laplacians and so on and so on. So we use a spectral method for this, spectral Crank-Nicholson. And this, by God, is the right answer with about 5% of the coefficients kept. And this is what you would get if you just chop wave numbers. It looks good, but it's wrong. You want to keep the oscillations. So this stuff works for vorticity. One of these is they're on top of each other. This is the truth. This is the sparse solution, and you can see we are keeping just these wave numbers and getting this solution. That's the point. We are just keeping these wave numbers and getting essentially the same solution as if we kept all the wave numbers. And therefore, you can do lots of nice things with sparsity. So this is really elementary sparsity because we're taking something which is sparse on a Fourier basis, and things stay diagonal. But this generalizes, we claim, without proof, nothing but arrogance, that sparse dynamics can approximate a wide range of dynamics. Sparse approximation. We have a nonlinear filter. The sparse computations allow for algorithms whose complexity is related to the sparsity level rather than the grid size. That's the point. So you can lower the computational effort by doing something really, really simple, at least in these cases. Take your favorite Fourier, take a Fourier method, update it, and if the solution is sparse in Fourier, apply soft thresholding, which is what this thing is, or shrinkage, whatever it's called. And it seems to work. I'll skip that. Okay, there's some references. There's a little bit of analysis, which I will zip through, which is somewhat on the pathetic side, but it's supposed to try to explain what's going on here. You know, I don't want to take, I have about 3 more topics, so, okay. So basically we have a numerical method like this, and we update it by first doing this and then doing this, period. Just doing this shrink nonsense, okay? But this looks more complicated than it is. I mean, this is a scalar problem. You just threshold, so it's easy. Okay. In principle, that would work in more complicated situations. Okay. So one more time. This operator you learn to love, I promise you, for many reasons. Okay. The order of convergence is now, I'll try to zip through this a little bit faster. Okay. So there's a little bit of convergence theory here, which I will not stress because it's very easy. It's basically triangle inequality. All this says is that if your update is a contraction, this doesn't screw it up. That's all. That's all this says. It's a very simple proof. It's really nothing to it. It has to do with the fact that soft shrinkage is a contraction. But at least it's something. So you can prove convergence if you're so inclined for some simple problems. But not too many problems have this nice structure. Okay. So consistency plus stability implies convergence. There's sort of a modified PDE analysis, which I like. And you're going to see more of that in the third part of my talk. That really comes up. What you're doing is really, the second step is taking argmin of this plus lambda times that. Okay, and so if you look at the PDE associated, the Euler Lagrange associated with that, the PDE looks like UT minus LU plus truncation error, plus, would you believe, the subgradient of the L1 norm of U. Ain't that cool? So you're associating a PDE with a subgradient of a variational problem. So it's a little bit unusual. That's what we're solving. It's a little bit unusual. This is the modified PDE. This I don't like, so I will skip. But I mean, if, God forbid, you did this, I would not be happy, but it's easier to analyze. So you replace L1 by something which is rounder, which is a bad thing to do computationally, it turns out. Okay. All right. Okay. Anyway, so there's one thing worth mentioning, which is a paper by Donahoe, which I will not talk about in great detail. But in 1995, before sparsity and L1 became a big deal, before compressive sensing, this paper doesn't even mention L1 as far as I can see, and doesn't mention sparsity. But good old David comes up with the idea that source thresholding is great, period. That's it. And there are reasons for that. So I will just echo that. You can more or less say it's some kind of near minimax. So source thresholding is a good thing. If you want to denoise, and if you want to basically get a recovered signal, then this is a good thing to do, and I will skip this stuff, but it's kind of fun. It's worth looking at. It's an interesting old paper, very highly cited. And again, he came up with this before, I think, the connection with L1 minimization was made a big deal of. Okay. All right. And basically what we do is get the first two terms in the asymptotic expansion in these homogenization type problems. That's what we seem to get, just by doing this very simple little thing. Okay, maybe I'll skip this. There's lots more to do, and I'll skip it. Okay, here's something which is another new topic. So everything I'm going to talk about today is basically compressive sensing connected with PDEs, would you believe, and physics, which is a little bit unusual, because usually it's with machine learning and imaging and things like that. And I'll do that kind of stuff at the end of the talk. But for the moment, let's talk about Hamilton-Jacobi equations. This is joint work with Jerome Darbon. He made a nice observation, which is the following. Okay, so compressive sensing, I should at least mention what it is. This is a big, big deal. This is one of the few times when the hype measures the reality, matches the reality. This really is a big deal. Compressive sensing, you want to solve AU equals B, where it's an M by M matrix, M is much less than N. You can't do it by looking for the sparsest solution, because that's NP complete. So nice results of Candes, Tau, Romberg, and Donahoe, and basically said that you can get the answer to this, the sparsest solution, by minimizing the L1 norm such that AU equals B. Okay, and so if you don't know that, it's an important fact, and it has changed the face of various topics in applied math. It really has. This simple little notion. So L1 optimization is a wonderful thing. And so what we did here is relate this to Hamilton-Jacobi equations. Okay? And the relation, and again, this is a work in progress with Jerome. The original problem is minimize the L1 norm such that AU equals B. There's a related problem. Add this term, which is a good thing to do. It turns out that if you add this term and solve this problem and everything is satisfies some hypotheses, I haven't told you what A is like, but A is the right kind of matrix. It's full rank. But it's M by n. It's a short fat matrix. If mu is large enough, the solution to this problem is the same as though this wasn't here. Okay? So by regularizing that a little bit, you get back the L1 minimum by itself without the L2 term. And that helps a little bit. This is not the same thing as replacing the V by a rounded thing. Not at all. This is very different. This is a good thing. Okay, so very quickly. Compressive sensing and Hamilton-Jacobi equations. All right. So here's the problem. Solve this problem such that AU equals B, or related problems where you regularize and just put a 1 over 2t over here. Aha, there's a t. This t is going to be time. This t is going to be time in a Hamilton-Jacobi equation. That's what it's going to be. And over here too, for that matter. So what you can do is show that this function, phi of bt, this is the, okay, I'm jumping ahead. This is the Fenchel dual, the original Hamiltonian, but it'll make sense in a minute, satisfies a Hamilton-Jacobi equation. So this is a little premature. Next slide should explain things better. Okay. To solve this problem, which is one of the ones we talked about before. For example, if H was quadratic, this would be the original compressed sensing problem slightly regularized. Okay? If H was this other crazy function, it would be some restriction to B minus A, BU less than T. The solution to this problem, which is a solution to a Hamilton-Jacobi equation, is given by this function, where Z is the augmin of this crazy thing. You know what the shrink operator now is. This is the Hamiltonian. You're solving this blasted PDE, phi t plus h of grad phi equals 0. So by solving this PDE, which you can do in 100 dimensions, curse of dimensionality is not a problem here, because the initial data is a little weird. The initial data is exactly the value phi of B0, which is the minimizer of this thing. So it looks like a cheat, slightly circular, but it's not, because here's the exact formula that gives you the answer. Okay? So here's a Hamilton-Jacobi equation in 100 dimensions that can be solved exactly. I mean, not exactly, numerically, and fast. But it has a very special initial data. But isn't it kind of cool? There's a link between Hamilton-Jacobi equations and compressive sensing. And it really exists. And this idea, by the way, led to a new numerical method, which seems to be the world champion, at least in my world, for solving this compressive sensing. You know, the basic problem, minimize the L1 norm of U such that AU equals F. So this also leads to a good numerical method for that, but it also is promising. Okay, this is for Craig Evans sitting here. If A were the identity, this would be almost a Riemann problem. The initial data for this thing would be, where is it? It would be U equals B, so it would just be the L1 norm of B, which is a Riemann problem. How do you like that? So you're solving a special Riemann problem 165 dimensions really fast in that special case. I think it's kind of cool that there's a link between these two topics, and there's more coming. Okay, so here we go. All right, so I'm... precisely transpose. Sorry. Okay, T, there's too many T's. Yeah, God. Okay, there's a T here and a T here, but okay. Good question. Okay. All right, so here we go. One more time. If H is 1/2 x squared, then you're solving Berger's equation. So you can solve Berger's equation in 155 dimensions or something if initial data is rather special. There's another case where you're minimizing this crazy functional, so B minus AU has to be less than T, and you solve this Hamilton-Jacobi equation. Okay. So something is going on here, which is kind of interesting. Okay. And it works for total variation. If you're a total lunatic, you can solve a Hamilton-Jacobi equation whose initial data is the TV of the independent variables in some crazy sense. It works in great generality you have this sort of generalized shrink, which is projection onto a space. There's a comma 1 over here missing, onto a unit interval. So it's a little bit technical, I'll skip it, but basically this whole theory works in general for any J of U. But there's great interest for things which are homogeneous degree 1, because those you can solve fast using our super duper Bregman, whatever it is, stuff. So there's some possibility of solving some interesting high-dimensional Hamiltonian. This is a control theory conference, actually, so maybe there's some interest in that. Okay. All right, onward. Okay, this is the next PDE topic, which is joined with Ozelin's Rongji, whose computer I'm using, Russ Kaflish. Okay. This is compressed modes for variational problems in mathematics and physics. Here we go. So for the 15th time, we want to find the sparsest solution of something. That's usually NP hard. L1 regularization is sorry, computationally tractable. And sparsity, at least in my world, was sparsity I think of as a discrete thing. You have a long vector and most of them are 0. But this guy Vidvid's, Ozelin's, walked into my office and said we should use sparsity to get functions which have compact support. How do you like them apples? So do sparsity on the x side and create functions which have small support and replace sines and cosines by those guys. How do you like that? The idea, which I'll show, but let me just say in words, you have Laplacian, the minus Laplacian plus v or something, and you have eigenfunctions. These guys, if v is 0, they're sines and cosines. These are not sparse, to put it mildly. Not at all sparse. But you'd like to use localized functions to approximate these guys. And that's a big deal in physics, apparently. So let me talk about that. Okay, what's analogous or sparsity? Continuous functions. How do you create sparse continuous functions? Okay, having satisfying certain things, of course. Okay, so here's something I just found out about 2 months ago. One-year functions were invented by a physicist. What they are is the following. You're looking at the function minus Laplacian u plus v, and you would like to replace the true eigenfunctions of this guy, which have wide support, by functions which are local, but whose linear combination or linear span of these local functions is very similar to the linear span of the true eigenfunctions. And thus, you can solve the problems using compact support functions and make linear algebra easy. Well, I can say anything up here, but that's the basic goal. Okay, so there's an approach which goes way back to do this, where they basically, I won't go through the details, but they basically rotate coordinates. First, they compute the true eigenfunctions, and then somehow they rotate coordinates and fool around a little bit to try to make them sparse. And it's not that successful. They have to cut off edges and stuff, and it's not a very convex, easy problem. They have to compute the eigenfunctions first and do that. We're going to skip all that. Okay. So basically, what they're trying to do is get orthonormal functions, which are a basis, and whose the first 10 of those, for example, span almost the same space as the first 10 true eigenfunctions. That's the goal. But they don't quite get it. And it's also, again, it's special and all kinds of blah, blah. So we're going to have a general way of doing this. And it seems to work. And of course, it involves L1. Okay? So it's so-called Kronig-Penning model. Well, here it is. Okay, so this is the true potential. So it's 1d minus Laplace, d squared dx squared plus v. V looks like that. Okay? So this is the true potential for positive ions in a solid material. This is a simplified model due to these two guys, Kronig-Penning. And for this model, you can almost write down the eigenfunctions by fooling around a little bit, because potential is piecewise constant. Okay? And these are the first 10 eigenfunctions. Now, if you have a sharp eye, you will see 10 different colors here. Okay? I'm colorblind, luckily, so. But there are 10 different colors here. Okay? And these functions are global. They're all over the place. Whereas, doing what we're going to do, well, that's not what we get. That's the initial data. That's it. These are the first 10 compressed modes that we get. Each of these things is only 0 and then starts over again, starts over. These are localized functions. These are localized functions whose linear span is almost the same as this guy. And it's not hard to find them. So that's the deal. And this was a big success. This is the first case we tried. Some other cases are harder. Okay, so again, we were solving Laplacian U plus that crazy sawtooth potential. And we solve it numerically, and I'll talk about that in a minute. And we generate the eigenfunctions for that, which are these. And then we do something special to get compressed eigenfunctions, compressed modes. They're not eigenfunctions. Okay. Okay. So these are the first n eigenfunctions of the true guy. And we're going to compare them to, what are we comparing them to? Oh, wait a second, let me go on to the next slide. Okay. Well, the punchline basically is the span of what we get is approximated by the span of the true eigenfunctions, the first n of these, which is going to be like 10, is approximated by the resulting span of what we get. But ours are sparse and localized. So we get functions which are mostly 0. You take 10 of those and compute the linear span and look at the eigenstructure of that, and it's almost the same as the true eigenfunctions, which are totally global. Okay? How do you do that? Okay, so if you wanted to get the eigenfunctions, the first 10 of those, you'd forget about this term. You'd minimize, this is basic stuff. The first eigenfunction would be minimize psi, h psi, such that this integral is 1. This is all we do. We add mu times the L1 norm of psi, and now I don't mean little L1. I mean big L1. Of course, you do it numerically, it's little L1. But anyway, it's big L1. So we're going to solve linear algebra. We're going to change linear algebra by replacing this elementary variation, or Rayleigh-Ritz, or whatever it is method, by adding sparsity. That's all there is to it. You add mu times that integral. And, for example, you can actually carry this out in some crazy case when the potential is 0. You can write down an answer, which has a little peak and stuff like that, which I won't talk about for the first eigenfunction. So you can recursively get a system of orthogonal functions this way, and we call these the compressed modes of the Schrodinger operator. Okay. So basically, to solve this, we were lucky that I just did something with Ranji, which was basically optimizing L1 type problems with on non-convex constraints like this. This is not a convex constraint. See, however, it's a constraint that's pretty easy to implement exactly. So we solved this problem over and over again by using this so-called split Bregman method, which turned out to be very much related to augmented Lagrangian and alternating direction method of multipliers. But it's perfect for L1 because of fast conversions and so on. So one more time, what we're taking, if mu weren't here, we would be solving for the eigenfunctions in a standard fashion, period. That's what we were doing. We're just adding mu to it. And we're seeing what that does. And what that does is sparsify the outcome. And it gives you functions that are approximate eigenfunctions, depends how big mu is, but are sparse. And we think this is going to be of interest in physics and linear algebra, actually. Okay. So there's a little bit of time, so Bregman iteration is again, we rediscovered augmented Lagrangian, but rewrote it in a different way. And you update, this is the convex function. This is the constraint you want to satisfy. This is the subgradient of the convex function. You subtract off from the convex function the linear piece, and you update this way, and it works like crazy for L1. It doesn't work like crazy for L2. There's something special about L1 that makes this stuff work. There's an error forgetting property about L1. There is an error because of this wonderful V. Because if two things are on the same side of the V, the Bregman distance is 0. And you converge, period. That's it. Next step, you're finished. So all you got to do is line the signs up right, and this thing converges. Anyway, but there's a step here which is not trivial, because what made this interesting is that we had this constraint, C transpose C equals 1. That made it a little bit harder, and we used it here. Okay. But again, the point of all this is to construct functions which are almost an orthonormal basis, but which are sparse, and which are solutions to a PDE, eigenfunctions to a PDE almost. Okay. So why not go a little bit further, as you will see, and actually construct a multi-resolution basis? This is wild. Coming up next. So anyway, this is the numerical method. For those of you who care, each step is simple. Okay. And I don't expect you to copy it. All right. But the fact of the matter is, when you solve this problem, every single step is either invert a linear operator, which is simple, like a discrete Laplacian, apply shrinkage, which is simple, and the one extra step is this projection onto the U transpose U equals 1, which is a little bit more complicated. Okay, so we don't have a proof of convergence because this is a non-convex problem. It would converge if we didn't have the U transpose U equal 1, but this makes it more interesting for our purposes. Okay. So here's the algorithm, which I'll skip. There's too much detail. Okay, so anyway, here are the eigenfunctions you get, which are supposed to approximate sines and cosines. Isn't that cool? Okay. So throw away your sines and cosines and use these localized guys. Every time a color changes, it means the support has ended. So they are compactly supported type stuff. And this is an easier case, which is the Kroning-Penny case, where you have a real potential. Okay, and 2D is going to be kind of interesting because it takes a long time before we'll be able to cover everything with these 2D guys. Well, we can do 2D, but we'll probably have to get a lot more of these functions for them to look like the true eigenfunctions. However, it's easy to do. Okay. And here is completeness of these guys. So here was the big triumph. They were right on top of each other for the first 10 for the Kroning-Penny. And they're pretty close as you go up. For 0 free electron case, they start going apart from each other. And this is the number of modes and so on versus and mu and so on. But we are pretty close to the true answers in the eigenvalues by doing this thing. And numerically, it's not that hard. It really isn't. Okay. Okay. So now comes something which is really daring, and I don't want to stick my neck out too far, but what we are looking at is functions which behave like wavelets, God help us, which are also eigenfunctions of Laplacian or Laplacian plus V or something. You do the same thing that we did before, except we want psi to be orthogonal to its translates. And it's not that hard. Again, it's not that hard to do. If you take a Fourier transform of this thing, it's a very easy thing to see to evaluate. And we call these things basic compressed plane waves. But the goal is the same kind of thing, to get sparse functions, but this time they're going to look like wavelets, that they are orthogonal to their translates. Okay. And maybe this is the numerical method, which I will skip. There's one step over here, which is easy, because Fourier transform diagonalizes that orthogonality constraint. Okay, so I don't want to get too much details, but this is what these guys look like. you can construct, this is level 1, then you can do level 2, level 3, level 4, and then take translates of these guys. And these behave like almost like a basis, which are, again, eigenfunctions of the Laplacian. Okay. So it's kind of unusual to get wavelet type things which are built on the eigenstructure of a differential operator. And that's what we're aiming at. And again, having sparsity in mind. So just to show you what it looks like, these are 20 of the first 4 modes. If you add up the wave number of all these guys, you get a nice covering of this vector. So it seems to be working. Okay. So that's probably it for, how am I doing time-wise? 10 more minutes? Okay. All right. So that's about that stuff. We did one special case, the Croning-Penny model, when you take one of those teeth and stick it way down, just to see what happens. And here's the energy of the eigenfunction. And this is what these guys look like. And also, it's kind of cute. There's a fast inverse transform for this thing. So if this really works, you can. We haven't proven completeness or anything, nothing. But this will be. There's a fast way of expanding in terms of these basis functions using Fourier transform. So we are slightly optimistic. Okay. And this is what the second lowest energy state is for that crazy model when you make the potential deep in one pool. Okay, so the basic idea is for this piece of work anyway, we have a variational method to create compressed modes as an analogy to sparsity to continuous functions. We have numerical methods which solve this non-convex problem with no theory, but we think it converges. We develop a set of localized orthonormal bases, and then compress plane waves and a fast transform. And there's a lot more to do about rigorous stuff. And now I'm going to try to find something. Okay. So that was kind of the differential equations part. Now comes some fun of image processing is always more fun in some ways. Okay, how do I get out of here? Escape. Okay, Finder. If I do this, okay. Here we go. Video compression. Enter. How do I do this? Click. What do I click? No. Beautiful. Okay. Thanks. Oh, I don't want the video from the beginning. I want to start from the beginning. Okay. Video compressive sensing. Okay. This is joint work with Hayden Schaefer and Yi Yang, who's sitting back there. Let's go. How far back should I go? You have a video, and this is now completely different stuff, but it's fun. And you want to compress it in real time, which means 2 things. First of all, you're going to subsample each individual frame, and then reconstruct using compressive sensing. But more importantly for us, we're going to skip frames. We're going to average frames. We're going to open the shutter and very wide if we predict that not much is happening. For example, if you're taking a video of a stationary object, you can obviously just go on forever. And instead of 30 frames a second, you can take a lot more. Or if it's mostly background and so on. So the idea is to predict that, and I'll try to show you how to do that. Well, we're going to use an adaptive compression rate. Okay, and I'll show you some results. Okay, so this is joint work. This is work motivated by some stuff going on at Duke by David Brady and a lot of other smart people who are building an exapixel camera, which was on the cover of Nature or something not long ago. So the initial data is the incoming data, not income. That's my mind works like that. Downsampled by 50%. Then the frames are averaged in time, and this is what you see. This is what you see. And you'd like to see something as good as the original. Okay. So you compress more when it's static and compress less when it's dynamic. And basically you use piecewise, you use polynomial interpolation to approximate the video velocity, because we want to do this real time, something really fast. And the polynomial interpolation is based on ENO, for those of you who know what I mean. There's some kind of essentially non-oscillatory thing which sort of tries to test gradients. But, okay, so it's related to the total variation. So anyway, here we go. Here's what the mask looks like. Let me say, click this thing, play, do something. Ah, it worked. Good. Okay, so that's the mask going up and masking half of the data, 50%. Okay, this is, can you see what's going on? Okay. All right, that's what you see. Okay. All right, let's try this one. This one's slow. That's the original. I hate this guy. Okay. All right. The next one. Okay, wait a second. Come on, you son of a gun. Why did it get stuck? And there he goes. All right, next one. Come on, come on, come on, come on. All right. Okay. So one more time. This is the compressed video. And that's what you will see. Okay. Oh, sorry. Go back. Those are the important parts of the compressed video, where the objects are moving. Come on. Video reconstruction. Okay. So we have a fancy schmancy way of doing this involving total variation of velocity and some interesting stuff in space. And here's the result. So if you want to see the original, God forbid, there it is. I mean, no, sorry, the reconstruction. So that is the reconstruction. So we go from that very messed up, with at least, I don't know, with lots of missing data to this. And if you look at it, you can see, over here somewhere, they tell me. Let me play it again. Start all over again. How do I restart? Let's see. Can I go back one and start all over again? No. Anyway, lots of detail is kept. That's the point. And in the next 3 minutes, I can probably show you how it works. Let me see if I can do that fast. Okay. No. Let's get out of here. Escape. Come on. Go down here. Okay, go up here. So just give you an idea of what the mathematics was behind it. Oops, come on, come on, come on, come on, come on. Ah! What am I doing wrong? I want to click on this. Okay. Every time I do that, it does that. It's your computer here. We can do that one if we have to. Okay, try that. Video, yeah, I'll do it. Okay. All right. I guess. Okay, that's not what I wanted, but let's see if I can find. Sorry. Anyway, let's go. Yeah, there should be some mathematics here. Hang on. Here we go. Sorry. Okay. All right. So again, we want to do adaptive temporal sample, compress redundant frames, real-time adaptation. So here's what we do. We have the ith frame. Kj is where the adaptation occurs. We have a sequence of these positive numbers. The stored frame is the sum of the frames between these two endpoints. Actually, it's the sum of the subsampled frames. The sum of the subsample frames. Okay. And we want to figure out how far we can stretch the shutter of this camera without making a terrible mistake, just by looking at what just happened. Okay, that's the idea. Okay. So we use the previous 4 frames and time points, and the output is the next time point, then it's a very elementary notion, which I kind of like. You use an adaptive polynomial fitting. You fit the first n-1 stored frames up to n-2, and then use the nth stored frame to compare it with the extrapolated previous stuff. And how can you figure out a smart way of saying, how far should I open my shutter? That's the question. And we do it globally. So if somebody opens a door, then we're up the creek, and they walk in. And you'll see that. But it still does a pretty good job. And what we do is something which I love, which is take an interpolation, we take a least squares fit, and we say whichever one of these guys is close to the true answer at the next step, which we have, we just computed, then we extend that and figure out how far to go. So we compare two interpolants. I love doing stuff like that. Trying to figure out how smooth something is. Okay. And we do that by taking small overlapping patches, and we have some kind of function value for each patch, so not enough time to go into detail. But the basic idea is right here. We choose the next step such that the difference is smaller than a given threshold. And we take a choice between these two different possible interpolants. And finally, we get stuff like this. Let's see if I can show you some results. Okay, so here's the original video. Play. Sorry. Oop. How come it doesn't move? Come on, baby, move. There it goes. This is fast. This is nothing but the original video. Okay, car moves in, blah, blah, blah. Okay. Next. Over here. Come on, Ben. Ah. How do I get to the next one? Oh, here it goes. I hope. Compressed video. Okay. Whoosh. That wasn't good. That thing came running in. But it didn't do a bad job, I mean, in my opinion. Everything was okay until that sort of got more than... But basically, you can predict how far out you can go. And you can do that with missing data and in real time, and that's probably the end of my talk. Okay, thanks.
So we have time for a few questions. Any questions?
Yep.
Pico.
Yeah. Yeah.
So I think you convinced me that I should be shrinking instead of truncating.
Absolutely.
So are there any cases where that is going to bite me, where the shrinking won't work?
Well, if you want to grow, no, joke. I mean, no, shrinking is, well, first of all, you might have asked another more interesting question. Why not use hard shrinkage? You know what that is? Yeah, you do. With turbulence, people use that. What they do is take the frequencies which are greater than something and keep them, and throw away everything else. And that's a bad thing. It's not as good as this. It's related to L1 optimization. And the reason it's bad is because it's discontinuous and it introduces artifacts. But your general question, no, shrinking is always good. It really is. I mean, it's the only difference between L2 and L1 is the old shrink. I promise you. And the same thing, the only difference between TV and Laplacian is total variation, which is curvature, you know, screwing around with curvature or screwing around with Laplacian. The only difference is shrink. So it's a wonderful operator. And people knew about it for a long, I mean, you know, it's been around for a long time. But.
Other questions? So if not, we thank Stan again. Thank you so much for